Hello everybody. Today we will be talking about the derivative function for calculus. So we previously talked about how to solve for the derivative of a function using the formal definition of derivative. So limit as h approaches towards zero of yada yada yada. But now what I want to do is I want to basically kind of like apply the whole derivative thing and see how does it actually work. So first we're going to start by talking about the main points over here. And the first one that comes to mind is that the derivative is a function that provides for the slope of any given point on the curve. So that's very important because at this point, some people might be asking, well, what's the purpose of solving for the derivative as a function? Like, what is it for? How do we use it? How do we apply it? And so forth. So this right here demystifies everything. The derivative, simply put, is to be able to solve for the slope at any point on the curve where the point is going to be, the x value of the point is going to be on the in the domain. So for example, you could use it to solve for the equation of the tangent line, solve for where you have a maximum, minimum, and so on and so on and so on. So the further we delve into it, the more application you'll actually see. But for right now, we'll just say that it's going to solve for the instantaneous slope. So here, the next part we can talk about a little bit further. We can now say that, let's say f of x is equal to y, is going to be our function. Then its derivative can be denoted by the following: y prime dy dx or f prime of x. So all of those three notations are very common in terms of if you're seeing, if you're asked to solve for the derivative, you can write it in any of those three notations. But more importantly now, I want to look at this black box right here, which is going to be the focus of today's lesson. Keep in mind that again, the derivative solves for the slope of any instantaneous point on the curve. So if f prime of x is greater than 0 over here, then that tells me that the slope is going to be positive. So which in turn tells me that the function itself is increasing at that point. So let me just go ahead and write that in here. So f is increasing at those values of x. So graphically, then that means that we would have something like this over here. So you can see all of this right here. F prime is greater than 0 because your slope are going to be positive. Now the next one is going to be f prime is less than 0. So using the same manner, then that tells me that the slope is going to be negative. So that means f is decreasing. Okay. So that's kind of like the second case in here. And for a graph like that, you'll probably have something like the following, where from this part to this part, that's where f prime is going to be less than 0. So finishing the trichotomy, we have increasing, we have decreasing, we have greater than 0, we have less than 0. So now what happens if f prime is equal to 0 or does not exist? So for a graph, for that to happen, that means that you have this scenario where you can see at this point, your slope is equal to 0, and the graph is going to yield a maximum over here. More specifically, we call that a local maximum. Then you can also have a scenario where the graph might be down here like this. So that could be a local minimum. Both cases will be where f prime is equal to 0. Okay, so we can have f achieves a local max or minimum. Okay. Now, for where f prime is going to be does not exist, there are different cases for it, so we have to be very careful. Some of the cases that we can see is that you might have a cusp like this, where you can see that the derivative does not exist at this point because there is no slope coming from the left. Oh, sorry. The reason why the slope doesn't exist over here at the cusp is whenever you're using the derivative function, or whenever you're using solving for the derivative, we're using limits. So that means that all the rules that we learned about limits have to apply. The limit coming from the left has to be the same as the limit coming from the right. So for cusp, it's a little bit harder because the slope coming from the left definitely does not agree with the slope that's coming from the right. From the left, it's saying it's decreasing. From the right, it's saying that it's increasing. So therefore, they're not the same thing. So this is a case where f prime is going to be does not exist then. Okay. Another case where f prime does not exist, it could be where you have maybe like say an asymptote. So meaning something like this, and then you have something asymptotic, and then the other part is going to be bottom part right here. So here f prime also does not exist. So it varies from cases to cases. But if you want to look at where you have just strictly the local maximum and local minimum, that you can guarantee on the fact that f prime is going to be equal to 0. Now, for the f prime does not exist scenario, you can have either one of those two cases. So you can't really determine if it's a local max or minimum in that case then. So we have to do a little bit further research. So now that we've talked about it, let's go ahead and see how we can apply all of this stuff right here. So in the first example, I want to sketch the derivative graph of the curve below. And what we're going to do is we're going to apply everything that we learned over here that we just came up with in this black box in order to figure out what the derivative is. The first thing that I would like to do always, and if I'm solving for the derivative, is to figure out where f prime is equal to 0, because that's usually the easiest case. So first, okay, again, look for where f prime is equal to 0, because that will then tell me that derivative is going to be equal to a maximum or minimum. That the original function is going to be a maximum or minimum. So here you can see at this value of x is equal to -1, x is equal to 1, and also x is equal to approximately maybe 3.8 or something like that. Those values, the derivative should be equal to 0 then, because remember, those are the maximum and minimum. You can literally see the slope is equal to 0. So over there, I'm going to go ahead and draw the point, right, 0. And then here we're going to have to also get 0. And then here we're also going to sketch out 0 then, okay? So the purple dot as of right now, those are where the derivative is equal to 0, because the slope of f is equal to 0. Now let's look at the rest of it. Look for the second part. Where is it increasing and where is it decreasing? Okay, so here, let me kind of write that here. So for the second part, we want to look for the following. If f is increasing, then f prime is greater than 0. And also similarly, if f is decreasing, then f prime is going to be less than 0. So we're just going to apply what we just said earlier. Now, let's go ahead and take this in sections. First, I'm going to look at this part over here. Everything to the left of x equals to -1. You'll notice all the graphs right there. You'll notice that portion of the graph of f is decreasing. So that tells me that the slope is going to be some negative number. Now, judging by the slope as to how steep it is, it's telling me that derivative is probably going to be like a pretty steep value first. It's going to be a large negative number, but then it gets smaller and smaller and smaller. The slope is like going from -5, -4, -3, -2, -1, and then eventually to 0. So graphically, for the derivative, you're probably going to end up with something like the following, where you have like -5, -4, -3, -2, -1, and so forth. So the sketch of the derivative will probably be something like this. Note again, all the values over here for the blue graph, those are going to be negative, which represents that the graph of the original, which is the red, is going to be decreasing. The next portion we're going to look at from -1 all the way to 1. Here you can see that the original graph is increasing, but it's increasing in a way such that we start with a slope of 0 and end with a slope of 0. So for the derivative graph, then that means that you're probably going to have everything that's positive first of all, and then it's going to increase and then decrease afterwards, because somewhere in the middle, maybe like where x is equal to 0, the slope is going to be at its greatest, okay? So that is just a sketch of the middle then. Next, for the other portion, we now look at from 1 all the way to like 3.4, somewhere around here. That portion, the graph is going to be decreasing, so that means the derivative is going to be negative. And just like the previous part, we start with a slope of 0 and end with a slope of 0. So putting it all together, if you start with a slope of 0 and end with a slope of 0, and all your slopes are going to be negative in between, the only way for me to be able to sketch a graph like that would probably be something like the following. And again, somewhere in the middle, that's where you have the steepest slope. So that means that the derivative should be the largest y value, or the y prime value. And finally, for the last part, everything that is greater than 3.8 or so. The graph of the original, the red, is increasing. So that means that the derivative should then be positive. So as it increases, as x increases, notice the slope is getting steeper and steeper and steeper. So that means the derivative, the value, is going to be a positive number, and it's going to get bigger and bigger and bigger. So that right there is going to be then the sketch of our derivative then. And note one special characteristics that's happening is if you look at the red curve, what we have to begin with, that looks like a quartic function, meaning that it's x raised to the fourth power. And it turns out that our derivative for this x to the fourth power equation is going to be something that is cubic, meaning x to the third power. And that is not a coincidence. In fact, in the later chapter, we're actually going to derive and show how that actually works out then. Okay, so it turns out that the derivative of a polynomial is always going to be one less degree of the polynomial. So we'll prove that later on. Okay, let's go ahead and try a couple more just to see how this actually works out. Now this graph, this one should look somewhat familiar to you guys because I'm just saying what is the derivative of the curve y is equal to sine of x. Now we couldn't come up with a way to solve for it algebraically, so maybe we can sketch it out using what we know already. Okay. So once again, the first thing we're going to do is we're going to point out or isolate where the graph is going to be at a maximum or minimum because those are where the derivative is equal to 0. So that's located here, that's located here, 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 and here, and here, and so on and so on and so on. So all of those places where I have a red dot, the derivative is going to be equal to 0. So I'm going to go ahead and put that in then. So here is going to be the first one, here's a second, here's a third, here's a fourth, here's a fifth, here's a sixth, and then here's a 7. And if it helps, I'll go ahead and write that in also. F prime is equal to 0, F prime is equal to 0, and so on and so on and so on. Okay, so that's where we came up with that idea. All right, so let's see. Oops, I guess I wrote the wrong notation, so I apologize. Let me go ahead and change that. Change this a little bit too. Okay, so F prime is equal to 0. F prime is equal to 0, F prime is equal to 0, and F prime is equal to 0. Okay, now let's look at what happens in between, okay? So first part, I'm going to go ahead and isolate maybe everything that is going to be increasing. So from this portion to this portion, right, you'll notice that F prime has to be greater than 0 because your graph is increasing. For the next part, this right here, where the graph is increasing, again, F prime is greater than 0. And for this part, F prime is greater than 0, right, because the graph is increasing. Whereas everything in between will then be decreasing then. So that tells me that F prime should then be negative. So here we have F prime is less than 0. We have here F prime is less than 0. And then we have now the last part, which is going to be F prime is also less than 0 then. Okay, and that now gives us an idea as to what the graph actually looks like. So put it all together. Okay, so let's see then. The first part looks like it's going to be from negative 2 pi to pi. That portion of the graph, F prime is supposed to be positive, and then afterwards, it's going to go from a slope of 0 to end with a slope of 0. So graphically, you're probably going to end up with something like this then. Okay, so that's going to be the derivative of the graph then. So you'll note again, right here in the middle, that's where you have the steepest slope. And so that means that the derivative is going to be at its largest value. The next portion, the entire graph is decreasing. So therefore, the derivative should be less than 0. And whereas the steepest slope, that's where your derivative is going to achieve the maximum. So that means you're going to go down and you're going to come back up. The next part is a repeat of what we had earlier because it looks like it's periodic. So the graph of this is going to be maybe something like this over here. And the next part, it's decreasing, so the derivative should be negative. Next part, derivative is increasing, so derivative should be, the graph is increasing, so the derivative should be positive. And then the last part, the graph is decreasing, so the derivative should be negative. And I'm hoping that you guys can see what's happening here. The pattern is that when I graph the derivative, it looks very similar to sine of x, which is what I'm trying to graph. But it's not quite sine, it's actually just kind of shifted over. Well, to be a little bit more specifically, this right here, if I graphed it out nicely enough, looks like it's going to be cosine of x. So from this conclusion, we can say that the derivative, right, y prime, if y is equal to sine of x, is going to be equal to cosine of x. So this we can kind of rely on for the time being, and we can show that as a proof a little bit later on. Okay. Now, let's go ahead and look at this last one right here. This is a harder example, but this is a very typical problem. maybe like say on an AP test or something, to ensure that you guys are understanding the whole concept of the derivative being the slope then. So here we have a piecewise function, and I would like to sketch out what the derivative actually looks like. So again, we're going to go ahead and do that in red. Okay. So first off, same idea as always. We're going to first look at where the derivative is equal to 0. So there are quite a few spots. One, I notice, is going to be everything before -5. You have a horizontal line, so that means that the slope of a horizontal line should always be equal to 0. So that's where the derivative is equal to 0 then. So it's just flat out that part. The derivative is not going to be found at x equals to -5 because it's not continuous, meaning from the left, the limit is not the same as coming from the right. So that's why it's not there. So next piece, in fact, I'm just going to go ahead and draw an open circle there. It's pretty safe to say that if your original function has an open circle, the derivative would then be an open circle as well. Because if the function is not continuous, you cannot find a derivative there. Next piece, for this part that looks kind of like cotangent graph. The graph itself is constantly decreasing, so that tells me the derivative should always be negative. And when we get to the middle of it, you have a slope that is smaller than all the other pieces around it. So when you get to 0, when you get to x is equal to 0, your slope is going towards -infinity because again it's decreasing. So that entire portion, right, from -5 to 0, we can say that f prime has to be less than 0 because the graph is decreasing. So putting it all together, we have an asymptote on the left, we have an asymptote on the right. So those slopes of the asymptotes are going to be -infinity. So when we put it together, my graph is probably going to look something like the following for the derivative then. Okay. So you can see how everything is going to be negative, which represents the value of the slopes are negative. But then it starts really, really big, like say -200 for the slope, -100 for the slope, -20 for the slope, and so on, all the way to the middle where the slope is probably not as big. But then eventually the slope gets bigger and bigger again. From 0 to 5, we have a slope that is equal to 1, it looks like, because it's a 1-to-1 ratio. We can now conclude that f prime over here is going to be equal to a negative number. More specifically, it's equal to -1 because that's the slope. So I'm going to go down here and I'm going to draw a horizontal line where the slope is equal to -1 numerically. Open circle on the left because it's not continuous over there at 0, x equals 0. And also an open circle on the right because if you notice, the slope does not actually exist. The instantaneous slope does not exist at 5. Anything that's after 5, from 5 to 10, f prime is supposed to then be equal to 1 because the slope is equal to 1 for the linear equation. So for the graph, we're going to go to 1, the value, and then just draw a horizontal line there. Again, on the left, there's an open circle, and then on the right, there's also an open circle because we don't know what's happening at the endpoints then. But there you go. That's going to be our graph of it. So this one, you might have to, have a little bit of time to let this all sink in because generally speaking, when I teach this section, I usually let my students do this for like 2 to 3 days. And this is just kind of like a quick overview of the whole thing. So this is definitely something that you're going to have to let it sink in. And in any kind of math class, as I like to mention, if you are going forward, you're going to have to know how to go backwards too. So that means that in order to get a complete mastery, what I would recommend is if you know how to graph, if you know what the graph looks like, you should be able to graph the derivative. And going backwards, if you are given the derivative graph, try to then figure out what the original graph actually looks like. All right, so thank you again for watching. I will see you next time. Have a good one.